So my name is B. Ravindhar, Assistant Professor in Department of EEE. Today we are discussing the course on Power System 2, and topic is sag in overhead transmission lines. So what is this? In case of transmission lines, we seen about the different type of parts, what are the elements and what is the tower structures and what is string efficiency, what are the different type of insulators. Those we discussed in last class. Today we will discuss about the sag and what is known as the span. And we see that we need to calculate the sag for a different conditions. So now we can see that what is mean by sag. So sag means a different level point of supports, and lowest point on the conductor is called sag. You can see that this is a pole and it is another pole, and for this pole we are this conductor is placed at these 2 points, and these 2 points it is connected by a conductor like this. And at this level supports, difference of this level supports and difference of between these two, this point is called sag. So means we can see that the sag means the level point of supports and lowest point on the conductor is called sag. And we can see that loading on the transmission line, while designing a overhead transmission line, from the mechanical point of view, they are made to withstand the worst portable weather conditions, that is loading on the transmission line. So you can see here some transmission lines which may be loaded by the weight of the conductor. First one is weight, ice loading and cross winds. So we have the 3 different loading on this particular conductor. We can see that here in this picture, it is having this particular conductor is having with a ice loading and also conductor weight, and there is a wind pressure. 3 loading will be there on transmission line. And what is mean by span? So span means the at these 2 particular poles, whatever the distance between these 2 poles is called the span. Whatever the conductor it is there, the part of overhead line between the 2 consecutive support is called span, and the horizontal distance between them is called span length. So this particular length we are calling as span length, and this span length will be vary based on the different level of voltage we are applying in transmission line or distribution lines. So you can see that in case of 11 kV distribution system, the span length is 100 meters for a 33 kV, and also it is having 100 meters. So you can see that between 2 poles it is having a span, this length is 100 meters, and 66 kV it is a 200 meter length, and 110 it is 250 to 300 meter, 132 and 230 kV transmission line may be having a 230 volt meter, 300 meter span length we can observe. And what is mean by sag means in practice, the line between the 2 consecutive supports followed this curved path we are calling as this maximum vertical distance in the span of overhead lines between the tight conductor and sagged conductor. So between these 2 tighter conductor and this sagged conductor, difference of these 2 at lowest point of this one, it is called sag. So we can define in another way. So that is the vertical distance in the span of overhead line between the tighter conductor, this tighter conductor, and this sagged conductor is called sag. And why this sag calculation is necessary in case of transmission line? Sag is due to its own weight. So whatever the conductor we are placing between these 2 poles, due to this one weight we are getting a sag, and sag determine the minimum ground clearance. So you can see that during different seasonal variations, this conductor can be it can be stretched, or it may be having some sag. So we need some clearance from the ground point of view, so that no one can be touched that particular transmission lines. So it is also depend on the line voltage. So based on the line voltage we require the clearances, and the larger sag makes the line more expensive. If you put a more sag, it is having a larger sag, then we require a more tower structure will be it required high height, and it required a clearance also we need to take care, then it may be more costly. So you can see that what are the different type of voltage levels and this sag in that meter. So 11 kV it is having a span in meters, it is maybe 100, and this 132 to 230 300 meter like that. Next we can see that another case is clearance from this ground. For any transmission line it is necessary to maintain clearance from the lowest point of the conductor to the ground. From this lowest point of this particular conductor to ground, we require a clearance. This is called ground clearance. It is called ground clearance. This ground clearance is required for any transmission or distribution lines. So suppose if you are constructing a building at this downstream, at this location, so that the transmission line, whatever the transmission line authorities, they will take a sign from that particular, whatever the land it is occupied, these particular places, no one can be construct any building at this particular location. So they will take a clearance from the local people. And if you are constructing some building here at the side of this tower, then also we need require some clearance from with respect to your transmission line. So they can give the some guidelines, and based on the guidelines, they can, whatever the land it is required for the erection of this transmission line, during the erection itself, they can take the clearance from the particular the whatever the landowners. And you can see that the clearance which is for the low voltage line, it is a 5.8 volt meters, and less than 66 kV it is 6 meters, and 66 to 110 it is 6.4 meters, 110 to and 166 kV it is 6.7, and once greater than 166 kV it is 7 meters. So you can see that variation of this ground clearance based on their operating voltages. And this tension on the conductor depend on the following factor: weight of the conductor, wind effect, ice loading, and temperature variation. So whatever this the tension on this particular conductor, we have the 4 factors, and then we can see that how we can calculate. While calculating the sag, there are 2 conditions. One consideration, one is when the supports are at equal ground level. So when the supports are at equal level, then we can calculate the sag. That is a one case. Another case is when the supports are at unequal level. So the supports are at unequal level. So like this, it is having one pole is here and another pole is here. So these are, it is at say hill stations. In hill stations, the whatever the ground it is having, it is at different levels. Then we require for that case, it is a different level supports. Now we need to calculate the sag when this lines are at equal levels. So we need to consider that a point A and B are at equal levels and having a span of length L, and the lowest point of this particular conductor is O, and tension of this conductor is, it is a tension of this conductor, and we are considering the arbitrary point at any point. Say I am taking the point P, at this point P is considered, and this coordinators are x comma y. So you can see that this particular at the midpoint we can get the lowest point, and for that case it is L is the total span, and L by 2 is up to this point, and x by we are taking the point x comma y, and we can see that at this case at middle of this particular this portion we are taking as x by 2, and it is the we are saying that the sag means this vertical distance. So we are taking y is the sag here, we are taking this at arbitrary point. So let O is the lowest point of the conductor, and L is the length span in meters, and W is the weight of the conductor per unit length, capital T is the tension of the conductor. So now we are saying that we are considering the point P at x comma y, and at this lowest point this tangential force will act like this, and whatever the weight of the particular conductor will act downwards. So if you are taking a conductor like this, this weight will be acted downwards, and the tension will act like this. So the point P on the conductor coordinates are x comma y, and this weight of the portion OP and acting downward at a distance x by 2 from the origin O, and the tangential tension T acting at a point O and equating the above 2 forces. So this tangential force, whatever we are having, this force and this downward force, both are acting at equal. Then we are saying that equating above 2 forces, T into Y. 2 into y equal to W into x is the weight of the conductor, and x by 2 is the distance we are considering. Then x by 2, then both are equating, then y equal from this W into x square by 2 into T. Now y is a sag at point P, so y is a variable point, and if it is moving up to the point B, then S will be the sag at point B. up to the point B it is a S, then S y equal to S, and x equal to nothing but if it is taking the half of this span length, then it is L by 2. Then if you substitute that relation S equal to W into x, L x means L by 2 whole square by 2 into T. Then we are getting as WL square by 8 into T. So S equal nothing but sag equal to WL square divided by 8 into T. So T is the tension, L is the span length, and W is the weight of the conductor. So that is a sag derivation in case of the transmission line having equal supports. Now supports are unequal level. So now we are having the transmission line at a unequal heights. So we are saying that at this point, it is a point tower A having this much of height, and the tower B is having this much of height. And this we can see that this conductor is having like this. And lowest point of this conductor is at this point, and we are taking that up to with respect to the pole A, the sag is S1. And with respect to pole B, it is the sag is S2. And difference of this two level supports, it is H. We are considering this one is the H is the difference of two heights of these two towers. And L is the span length. And we are considering up to the point O, lowest point, it is X1. And from up with respect to B, it is X2 is the span length. So the position of this lowest point O of a conductor, which is not exactly at center of the distance. So what we are saying that when the towers are at equal height, then we are getting it midpoint. But when the tower heights are unequal heights, we are getting at different positions, and it is not at center. So X1 is the distance of support at lowest level, that is from A to the lowest point O, and X2 is the distance of support at higher levels B from the lowest point O. And L is the span length, that is X1 plus X2. L equal to nothing but a span length, and that is equal to X1 plus X2. And H is the difference in the level between two supports. And T is the tension in the conductor. And so H is nothing but S2 minus H1. So that is the difference of two level supports. We are getting as S2 minus S1. And if W is the weight per unit length of the conductor, then we can calculate the sag. We know that S1 equal to Wx1 square by 2T, and S2 equal to Wx2 square by 2T. In case of the relation, we are getting the sag relation, then S equal to Wx square by 2T. In that relation, we can keep that if it with respect to the pole A and with respect to pole B. Then difference of this S2 minus S1 is nothing but W by 2T into X2 square minus X1 square. This X2 square minus X1 square, like A square minus B square, that we can write as A minus B into A plus B. Then we can write this S2 minus S1 equal to W by 2T X2 minus X1 into X2 plus X1 equal to H. So that your S2 minus H1 nothing but H. Then we are writing here equal to H. Then it is X2 plus X1 plus X2. We know that it is a span length, it is L. So then if you substitute that X2 plus X1 equal to L, and if you substitute in that relation, then this W by 2T X2 minus X1 into X2 plus X1 equal to H. Then it is here it is L. If you write here it is L, then it is W by 2T into X2 minus X1 into L equal to H. From this relation, we can get X2 minus X1 equal to 2T into H divided by W into L. So that is X2 minus X1, and we know already that X1 plus X2 equal to, and this X2 plus X1 equal to what? We got L. And solve these two equations, this equation and this equation. If you solve, then you can write like this. If we solve these two equations, that is X2 plus X1 equal to L and X2 minus X1 equal to 2TH by WL. If you add these two, then it is 2 are cancel out, then 2x2 equal to L plus 2TH divided by W into L. Then you can get x2 is nothing but L by 2 plus TH divided by WL. Similarly, if you take x2 plus x1, it is x2 minus x1 equal to 2TH divided by W into L. Then if you take minus, then it will be plus, then it is minus, then we can write here. So it is x2 get cancelled, and this is 2x1, 2 into x1 equal to L minus 2TH divided by W into L. From this x1 equal nothing but L by 2 minus TH by WL. So you can get x1 and x2, the 2 point we can get from this. So that is the relation we are getting. X1 is nothing but L by 2 minus TH by omega into L. X2 equal nothing but L by 2 plus TH by omega L. And substitute this equation in your SAG calculated equations, that is S1 equal to Wx1 square by 2t, S2 equal to Wx2 square by 2t, and these formulas are at normal temperature and still air conductor acted only its own weight. So like that we need to calculate the SAG when the supports are at unequal levels. Next one is effect of ice loading and wind pressure on the SAG. So till now we didn't consider any wind effects or ice loading on the particular conductor. Just normal conductor weight we are considered. Now we are considering that there is having this particular conductor, it may be effect with the wind and also the ice loading. So we can see that it is a normal conductor it is having, and this conductor having a diameter is D, and this particular conductor is coated with the ice. So this much of coating of the ice it is there, so it is a ice coating, and that thickness of this particular ice we are considering as T. So D is the diameter of the conductor, T is the thickness of the ice coating, and we can see that the conductor having this conductor and ice weight total, whatever this, it is a conductor, whatever the ice is there on the particular conductor, and this weight will always act downwards, and the wind pressure will act like this. This means the wind pressure will be acted in horizontally like this, but the whatever the weight and ice loading will be acted downwards in vertically. Then we are considering that the weight, wind of the weight is, we are considering here the wind weight is like that. So wind weight we are considering vertically in the horizontal direction WW, and weight of this conductor as well as ice, it is acted downwards like this. So it is the weight of the conductor, Wi is the ice weight. Then resultant of these two weights we are considering as total weight which is acted by that particular conductor. So it is a total weight. So normally the net wind pressure direction is taken into the horizontal direction to the line conductor. So horizontally we can take the wind loading, and direction of ice coating and the original conductor weight pressure in the vertical direction. So then total force on this high voltage line conductor is the vertical sum of these horizontal and vertical forces. So total weight of this conductor per unit length we can calculate it as WT equal to, so W plus WI whole square plus WW square. So whereas this W means the weight of the conductor per unit length. So weight of the conductor per unit length, okay, unit length how much weight is there, that we are calculating. That may be sometime it may having conductor material density. So whatever the material it is used, he may give the density, and into volume per unit length, and we have to calculate with respect to volume, then also we can calculate the total weight of the conductor. Next is Wi is the weight of the ice per unit length. Weight of the ice per unit length, that can be calculated as density of the ice, how much density is there, and volume of the ice per unit length. So density of ice into, and this volume of the ice is nothing but, we can see that it is a conductor and it is a ice coating. It is a thickness T and it is a diameter D. So total diameter we can see here, this total diameter we need to calculate it as this. So it is a conductor and it is the thickness of this one. Then this total diameter is nothing but, it is a D and it is a T and T. So total we can see that D plus 2T. total diameter is d plus 2t. This diameter whole square minus this particular conductor diameter, if you remove, then we can get the ice coating. So then we can see that pi by 4, this volume of the ice per unit length is nothing but area into length. That is pi by 4 into d square into 1. So 1 per unit length. Then pi by 4 into this d square is nothing but d by 2 d plus 2t whole square minus this d square minus d square. So this is the value we can calculate into 1. Then if you say d plus 2t means d square plus 4t square minus 4 dt minus d square. So d square get cancelled. Then we can get as this, further we can write as, so it is plus, then it is 4 t, if you take common, then it is t plus d into pi by 4. So 4 cancel, then it is pi into t plus d. So that is the relation we are getting here. So density of ice into pi into t into d plus t is the volume of the ice. From that relation we can get it, so that we can calculate the weight of the ice on a particular conductor. Next is wind force per unit length. So wind force, how much it is acted per unit length, that is the wind pressure per unit area into projected area per unit length. So projected area, again we can calculate it is, so it is a d plus 2t total area, it is projected area plus per unit length. So wind pressure into d plus 2t into 1. So d plus 2t into 1 is the area we can calculate. Then wind and ice loading effect, if you are considering the conductor set itself at an angle of theta, then the vertical sag, so you can see that it is a theta. So this vertical sag, how much it is there. So the vertical, till previously we calculated the sag, and that sag is WL square by 80, and in that relation we didn't considering any this ice and wind loading effect. Whenever this ice and wind loading effect is there, we need to calculate the vertical sag. So this vertical sag, from this relation we can see that here it is the sag and it is a theta which is there, and we need to calculate this vertical sag. That vertical sag is nothing but tan theta. So this relation we know that from this, so it is your wind loading, and it is the W plus Wi, and resultant of these two, then it is a theta. If you are taking, then tan theta is nothing but, from this relation, tan theta equal to WW by W plus Wi. So the sag in the conductor is given by S equal to WL square by 2T. S is called slant sag. This S is called slant sag, and if you take the theta for this, the vertical sag is nothing but, so if you write here tan theta equal to S divided by this vertical cos theta, from this cos theta equal to nothing but, we can calculate it as vertical sag divided by S. From this vertical sag is nothing but sag equal to S into cos theta. So that is your vertical sag what we calculated. Next, another relation that is about the sag with respect to this vertical sag, and what is known as this how we can calculate the effect of wind and ice loading in a sag calculation we calculated. After calculating this total weight of the conductor, then you can calculate the sag. So next, another relation we have the string chart. What is mean by string chart, and what is the use of this string chart? And it is useful in knowing the sag and tension at any temperature. We need to calculate the sag and tension at any temperature. It will be possible. It gives the data per a sag to allow the tension to be allowed for a particular temperature, and string chart is prepared by calculating the sag and tension on the conductor under worst condition, and such as maximum wind pressure and also minimum temperature by assuming the suitable factor of safety. So if there is a worst condition, it is having, say, high wind is there, then how the this transmission line, whatever the sag, it can be affected. And also minimum temperature variation is there. So minimum temperature variation means, say, only 25 degrees is your room temperature, it very less temperature variation, then what will be the safety issues we need to calculate it. Next, we can see that in this the string chart, we can calculate this tension and sag with respect to temperature. As the temperature increases, how this sag will be there. So as the temperature increases, sag, what will happen as the temperature increases, sag also increases. We can see that as the temperature increases, the sag gets increases. Sag also increases. And next is, as the temperature increases, what about the tension? The tension gets decreases. Tension gets decreases. So then we can see that if you are designing a transmission line at 25 degrees temperature with having this sag and how much tension we can calculate. Later that how the temperature is, say, 40 degrees or say 10 degrees, how the sag and tension it will be their effect on the transmission line, we can calculate. And the graph of tension versus temperature and sag versus temperature can be plotted, and this graph will be plotted for a fixed span, and it is called string chart. So that is the use of this string chart. So on the minimum temperature variations, how this string chart can be affected. The tension on the conductor is maximum. When minimum temperature is there, then tension in the conductor is maximum. When the temperature is minimum and wind pressure is maximum, then tension is nothing but, we can know that breaking strength by this factor of safety is 2.5. And maximum temperature is produced when the temperature is maximum and there is no wind pressure. So that is about this sag and what is meant by string chart. So one more point we need to discuss, that when the sag is very high, when sag is very high, what will happen? So if you are having the more sag, so it is having very high sag, then we required the more this transmission line structure, it is required more complexity, means it is a more transmission line erection, it is required costly, and the ground clearance is, now you can see that it is having a minimum, that will be more effect. So next is, as the temperature, we can't maintain the this transmission line is very high sag. Okay, next low sag is there. What will happen if you are maintaining the transmission line with having a no sag? Then what will happen? So you can see that when we are having the low sag, when temperature variation is there. So during the say during rainy season we are not having any variation, but when winter it comes, this conductor gets very tight, the tension gets increases. As the temperature increases, tension gets increases. If you are maintaining the sag is very tight, this conductor may be break. Okay, so don't make your transmission line with a minimum sag. You have to keep minimum sag. If you are not having minimum sag, the conductor may be break. That is the one point. And it is having the higher sag, then if the temperature increases, this tension get decreased, and it may be the contact can come near to the ground. That is another problem. So like that we are having, and this temperature variations also we need to take care. Then we don't maintain the transmission line with a high sag or no sag. So you require a minimum sag. So that is about the sag we discuss today class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.